Hello and good afternoon. I'm Jennifer Arroyo, Editorial Director for Electronics Cooling. On behalf of the producers here in Philadelphia, welcome and thank you for joining us at Thermal Live. Next up today, we have a presentation given by Metodi Slatinov and Denver Shaferzik, Technical Lead of R&D and Director of Engineering, respectively, at ERG Aerospace. In their presentation, Metodi and Denver will be diving into the characteristics of metal foams and introduce the principles behind designing effective metal foam cooling systems. I want to take a second to encourage you all to submit your questions throughout their presentation into the Q&A panel on your screen. Our speakers will do their best to answer them all at the end of the presentation. Also note that you can download the slides in the download section of the audience console. So without further delay, please welcome Metodi and Denver.
Thank you, Jennifer, and thanks to everyone joining us today. Metodi and I are pleased to discuss heat transfer with metal foam. I will begin with an introduction to metal foam and how it fits into the world of heat transfer. Metodi will then dive into the details of the unique properties of this material, the recommended approach to designing with foam. I'll continue with a range of options for fabricating and integrating foam into a final product. And Metodi will conclude with case studies illustrating some of the most common heat transfer applications using metal foam. The most common question we get asked, and I'm sure a question some of you are wondering yourselves, is what is metal foam? To put it simply, it's a rigid sponge made of metal. There are numerous types of metal foams, and they have a huge range of applications. Since we're focusing on heat transfer today, we're going to focus on open-celled metal foams, which consist of an open network of interconnected ligaments that form cells with open pores. Some of the relevant features of these types of foams include their high thermal conductivity, high surface area to volume ratio, and local heat transfer coefficients. The ability to customize the foam structure and fine-tune its properties, and some of the unique opportunities from a manufacturing perspective with metal foams. For example, they can be machined or formed into conformal shapes. Typically, metal foams come into play in heat transfer applications as a higher performing alternative to current fin technology. Metal foams can be applied across the full spectrum of thermal management schemes, from natural convection heat sinks to two-phase and phase change material cooling. As power electronics trend toward generating more waste heat in smaller packages, our goal as engineers is always to use the simplest solution for the application at hand. The high performance of metal foam can significantly extend the range of applicability for a given cooling scheme. Metal foams perform well when current technology doesn't quite provide enough cooling. Metal foams work particularly well when there are unique constraints on form factor, such as low volume requirements, low profile requirements, or conformal geometry constraints. Metal foams should be considered when heat fluxes are high and there is an advantage to simplifying the cooling scheme. For example, replacing liquid cooling with an air-cooled system, or replacing a two-phase system with a single-phase cooling system. Another area for consideration with two-phase flow is when pool boiling or flow boiling are indeed required. Using metal foams, high surface area and ability to disperse the phases and prevent departure from nucleate boiling or dry out result in higher heat transfer coefficients and critical heat fluxes for a more efficient cooling system. Metal foam also performs well in solid to liquid two-phase systems, typically referred to as phase change material or PCM heat exchangers. In PCM heat exchangers, high peak thermal loads are absorbed into latent heat as the PCM melts, while metal foam matrix provides crucial enhancement to the structure, increasing thermal conductivity, allowing very uniform temperature profiles throughout the melting process. Metodi will circle back to talk more about specific applications that demonstrate metal foam in action later in today's talk. Let's turn our attention back to understanding the structure and properties of metal foam. At the macro level, metal foam is simply a type of porous medium containing open space, or voids, and solid structure, or the matrix. Numerous other materials fit the broad category of porous media, including different foams, but not all of them are relevant to heat transfer. Some of these include sintered metal structures, packed wire screens, honeycomb, and even your conventional fin technology. Although here we are focusing exclusively on open-celled metal foams with solid ligaments, the fluid mechanics and heat transfer principles are the same for all porous media, and they can be researched and analyzed in a very similar way. One of the most fundamental characteristics of a porous medium is the fraction of open space termed porosity. In some cases, it's easier to think about the inverse of that, the volume fraction of solid matrix, often referred to as relative density, since in practice it is measured by taking the ratio of the bulk density of the porous media to the density of the raw material of the same solid matrix. Relative density is a primary driver influencing the thermal and flow properties of any porous medium. But there are a number of other factors that come into play as well, and those are more specific to porous structure under consideration. In the world of metal foams, they aren't all created equal. Duocell foam is unique among open-celled foams. Duocell has solid ligaments of the parent alloy, and its physical and thermal properties can be customized across a very wide range. First, the appropriate parent material can be selected based on the thermal and chemical compatibility requirements. Some of these options include aluminum, copper, Inconel, stainless steel, and ceramics. Then, the pore size and ligament cross-section can be independently controlled to fine-tune the desired surface area, pressure drop, and metal volume fraction. Pore size is typically described by the number of pores per inch, or PPI. For pore size, I like to think of them as soccer balls. A higher PPI, for example, 40 PPI, means more and smaller soccer balls. A lower PPI, like 5 PPI, means fewer, larger soccer balls in a given volume. Meanwhile, as the metal volume fraction, or relative density, increases, the ligament cross-section changes from triangular to circular. This increases both the conduction area and surface area in a way that is completely independent from the pore size. Last but not least, and unlike hollow ligament metal foams, Duocell can be compressed by a factor of 6 or more without fracturing the ligaments. This makes it a practical way to drastically increase the surface area and increase effective thermal conductivity in a given volume.
In the following section, we will dive deeper into the characteristics and properties of Duocell metal foam. We will start with characterization of the structure or morphology of the foam. For heat transfer, we are specifically interested in surface area, cross-section area, cell size, pore size, and ligament thickness. Knowing these characteristic area and length scales is critical for correlating experimental data, as well as for interpreting such data for design. And while the randomness of foam can seem daunting, the advent of computed tomography, or CT, has really transformed our ability to rigorously measure these features in a statistically meaningful way. Just as in a medical CT scan, we can reconstruct a three-dimensional model of a foam sample based on a stack of X-ray images taken at incremental slices through the material. We can then deploy algorithms to separate and measure features of interest, tally distributions, and extract statistics. For example, on the far right image, we have segmented the foam structure by cutting ligaments at the minimum cross-section so that we can measure ligament thickness in an automated and consistent way. Here we have some representative numbers. On the leftmost plot, we're showing surface area per unit volume, sometimes referred to as specific surface area, as a function of relative density. The two curves are for 10 and 20 PPI foam respectively. Recall that PPI stands for pores per inch, so 20 PPI has a smaller pore size and consequently greater interfacial area. The remaining plots are for cell size, pore size, and ligament thickness respectively, all plotted as functions of nominal pores per inch. Note that while cell size is purely a function of PPI, pore size and ligament thickness are progressively more dependent on relative density as well. This is because the way we control relative density is by thickening the ligaments. You can see this in the spread of the data points for 20 PPI, which are from samples spanning a range of relative densities. Not shown on this slide is data for cross-section area. That is because we can demonstrate analytically and confirm through measurement that the cross-section area in 2 dimensions is equivalent to the metal volume fraction, or relative density, in 3 dimensions. Note that the specific surface area shown on the previous chart was for as-manufactured uncompressed foam. Subsequent mechanical compression is a great way to dramatically increase both surface area and conduction area, as exemplified by the 2 photographs below. Here I apologize for mislabeling the images. The one on the right is clearly compressed. Unlike hollow ligament foams, the solid ligaments of duocell are highly ductile, allowing duocell foam to be compressed mechanically by a factor of 6 or more, with a proportional increase in surface area and thermal conductivity. During compression, the individual ligaments will buckle without fracturing, resulting in the distinctive crush plateau in the stress-strain curve shown on the right. The 3 curves here correspond to 3 different starting relative densities. It is not unusual to target a 40+% relative density by starting with a 7 or 8% density foam and compressing by a factor of 6. There is an important nuance about controlling bulk thermal conductivity of foam through compression, and we will address that momentarily. But first, let's consider the thermal conductivity of uncompressed foam. The plot on the left shows experimental data for aluminum foam as a function of porosity. It turns out that you can fit a surprisingly simple yet intuitive model to this data. If you consider that foam is a 3-dimensional structure of interconnected ligaments, and that on average 1/3 of those ligaments are aligned with the heat flux direction, it is perhaps not all that surprising that the effective thermal conductivity of foam equals 1/3 times the metal volume fraction, frequently written as 1 minus porosity, as in the equation here, times the thermal conductivity of the base alloy. Uncompressed foam can be produced with thermal conductivities of up to 10 or 15 watts per meter Kelvin for aluminum and copper respectively. But as noted on the previous slide, we can increase this dramatically by mechanical compression. Copper foam compressed to 40% relative density can achieve thermal conductivities of 50 watts per meter Kelvin. However, it is absolutely crucial that one applies the compression perpendicular to the heat flux direction. When you compress foam, you increase the number of conducting ligaments per unit area in the 2 orthogonal directions, thereby increasing the effective thermal conductivity proportionally. Yet, along the compression direction, not only are the number of conducting ligaments staying the same, but the conduction path actually becomes highly tortuous, like a compressed noodle. So, the effective thermal conductivity actually decreases dramatically along the compression direction. This is a common pitfall, especially since normally the heat flux direction is by far the thinnest dimension of the foam core. It is essentially your fin height. It is tempting to just press the foam down to this small thickness, but in fact, you would be shooting yourself in the foot from a thermal performance perspective. Instead, one should compress a larger piece of foam and then slice it to the desired thickness or fin height in the appropriate dimension. In addition to the high surface area achievable with small pore and compressed foams, the great advantage of metal foam in the heat transfer arena comes from its exceptionally high local heat transfer coefficient. Due to the small length scale of the ligaments, the boundary layer is continuously being disrupted and restarted. A high degree of mixing further augments the heat transfer coefficient while also promoting thermal dispersion. The latter helps mix out thermal gradients in the fluid, as illustrated with the sketch on the right, and has the effect of increasing the effective thermal conductivity of the fluid. Overall, the convective heat transfer mechanism can be thought of as analogous to extremely small cylinders in crossflow. Indeed, most correlations in the literature take a similar form. However, it is to be noted that the correlations in the open literature are to be considered with extreme caution due to the inadequate characterization of length scales and surface area, inconsistencies in data reduction, and non-optimal experimental setup. For example, to our knowledge, there is no published data for compressed foam that has been reduced correctly and takes into account the importance of compressing perpendicular to the heat flux direction. Lastly, one must usually consider the flow resistance or pressure drop through the foam. Experimental data for fins and other conventional extended surfaces is usually cast as a friction factor. While the same can be done with foam, more convenient correlations make use of porous media theory. Pressure drop in porous media follows a quadratic form of the Darcy equation, where U is the superficial or approach velocity of the fluid. The linear term represents friction losses on the wetted surface and is characterized by the permeability constant K. This term usually dominates in low Reynolds number regimes. The quadratic term represents form drag losses due to the wake behind each ligament, and the constant C is referred to as the form drag coefficient. This term dominates at high flow velocities. Both K and C are determined by fitting a quadratic curve to experimental data, and both constants can be correlated over a broad range of foam configurations, including the effect of pore size, relative density, and compression. Now that we have a good grasp of the characteristics and properties of metal foam, let's talk briefly about how to approach a typical thermal design problem, how standard heat transfer analysis methods apply to foam, and ways in which designing with foam differs from designing with fins. For simple one-dimensional configurations, or for first-order analyses, classical fin theory can be applied. Consider the fin and foam cores depicted above. Since heat is applied from both top and bottom, in the subsequent discussion, the effective fin height, or foam thickness, is essentially half the plate spacing. In both cases, you can express the heat flux using Newton's law of cooling, with the fin efficiency term accounting for the fact that the temperature distribution along the length of the fin is lower than the base. The fin efficiency can be derived analytically and is a function of fin height, surface area per unit volume, and bulk thermal conductivity of the porous matrix. For very simple geometries, such as straight fins, you can further simplify this to arrive at the expression commonly seen in textbooks, which contains fin geometry parameters and parent material thermal conductivity. But with foam, we just use the more general expression along with empirically determined surface area per unit volume and bulk or effective thermal conductivity. Applying fin theory in this way, we can get a sense of the performance and design space for foam heat exchangers. It is most informative to look at the performance in terms of an overall effective heat transfer coefficient as a measure of how much heat you can pull out per unit area for every degree of temperature difference between coolant and heated surface. This can be compared to a flat plate heat transfer coefficient to get a sense of the enhancement due to foam. The surface plot on the right shows the effective heat transfer coefficient as a function of foam thickness and relative density. Here we have assumed a 30 pores per inch copper foam and a constant value for local film coefficient that is representative of water-cooled foam. Note the range of effective heat transfer coefficient on the vertical axis. A foam configuration with an effective heat transfer coefficient of 50 watts per square inch per degree C would pull out 1 kilowatt of heat per square inch given a 20-degree temperature difference. And this is just with single-phase liquid cooling. Another thing to note is that for liquid-cooled systems, the optimal fin height of the foam core is usually on the order of 0.1 inches, since beyond that point, performance saturates due to fin efficiency effects. For more complex configurations, computational fluid dynamics can be employed. Resolving the actual ligament structure with mesh would obviously be prohibitive for anything other than fundamental research on a very small scale. But for design, it is quite straightforward and computationally efficient to use a porous media approach, where the foam is modeled as a permeable block of material with user-specified properties such as bulk thermal conductivity, permeability, specific surface area, and heat transfer coefficient. Here, this is demonstrated on the same one-dimensional problem that we solved analytically on the previous slide. And indeed, you can see that the temperature profiles predicted by CFD match those from theory. The same approach can be used to tackle more complex problems with multiple heat sources and detailed manifolding. So far, we have highlighted the similarities between designing with foam versus designing with fins. I would like to close out this section by pointing out one aspect of designing with foam that may require a bit of a change in mindset. As you might expect, the high degree of mixing that so enhances thermal performance in foam also comes with a higher pressure drop. Fortunately, the pressure drop concern can be mitigated by reconfiguring the inlet headers, or the cores themselves, to direct the flow across the wider dimension of the foam core, thereby reducing flow velocity. Since flow resistance scales much more strongly with velocity than does heat transfer coefficient, pressure drop can be managed in this way with minimal sacrifice in heat transfer performance. This design philosophy is not new. The diagrams here of oblique headers and folded cores are from the canonical heat transfer text by Case in London. The approach is also used in other areas of engineering, such as this labyrinth spillway on a dam, or even the HEPA filter in your household vacuum machine. Yet more conventional thin cold plates and heat exchangers do not usually resort to such architectures, and indeed in many cases they're precluded from doing so due to the unidirectional nature of fins. Therefore, when one is considering a drop-in replacement with foam, it is useful to think out of the box in terms of the form factor and manifolding, and make the best use of the foam's advantages.
Now, let's take a look at the practical matter of fabricating real products with foam. Earlier, I mentioned that duocell metal foams are rather unique in the open-celled foam world. These foams are manufactured by ERG Aerospace. ERG has been making duocell since 1967 and specializes in integrating it into high-performance systems. ERG is a small company that is vertically integrated with a history of making prototypes and one-off designs, as well as high production runs for products for various industries. ERG's experience in industries like aerospace, commercial, defense, semiconductor, and biomedical allow unique solutions to complex problems. With our experience in both manufacturing the foam and designing with the foam, we can drive designs quickly that integrate duocell metal foam to high-performance products. This helps reduce prototype and development cycle times during products' life cycles, allowing them to go to market faster. Part of the uniqueness of duocell is the ability to process it into many different shapes and sizes to meet the demands of a broad range of heat exchanger designs. Through our 53 years of working with the material, we've developed processes and systems for shaping the material using bandsaws, CNC equipment like mills and lathes, and pressing dies for complex shapes. Surface treatments can also be applied to the metal foam and include anodizing, plating, and chemical conversion coating. For example, Surface treatments that work for 6000 series aluminum also work for duocell metal foam made from 6000 series aluminum. Duocell metal foams can be integrated into the final product or housing via processes like brazing, soldering, or epoxies. Since the focus of today's talk is on heat transfer applications, we'll dive more into the thermal and mechanical interfaces via brazing and soldering. Vacuum brazing and dip brazing are both used routinely to eliminate contact resistance while ensuring a strong joint and high thermal transfer from the housing to the metal foam matrix. For situations where mechanical strength requirements are a little less stringent, soldering can be used to create a thermal interface that is just as good, but at a lower cost. Soldering is also particularly great when it comes to copper foam. Other low-cost alternatives include various thermal adhesives, such as epoxies and tapes. While these do introduce additional thermal resistance, they can be great options for lower heat flux applications, such as natural convection heat sinks, where the relative significance of that increased resistance is much less pronounced. On the other hand, for applications where every degree matters, the unique characteristics of metal foam create opportunities for eliminating the highly resistive thermal interfaces of soft materials, including thermal pads, pastes, and thermal epoxies that are commonly used to couple discrete electronic devices. Metal foams have a very high effective compliance. This allows metallurgical bonding to the foam by soldering or brazing to low thermal expansion or low CTE materials like metallized ceramic plates, low expansion composites, among others. Since this CTE mismatch-related thermal stresses and deformations are limited, the reliability of the heat exchanger and thermal base is not compromised, as verified by hundreds of thermal cycles.
Finally, let us look at some actual applications. Finned heat sinks, either natural convection or fan-cooled, are ubiquitous in everyday electronics cooling applications. Foam can be incorporated into a heat sink, either as a complete replacement of fins or as a hybrid fin-foam solution. Each approach has its own place, with the former unlocking new opportunities for extremely low-profile or even conformal heat sinks, while the latter is a great way to significantly boost performance in the conventional design space of extruded fins. Recent research into jet impingement cooling has also shown great promise for augmenting heat transfer by over 200% when a layer of foam is incorporated into the target surface. When an air-cooled solution is inadequate, a liquid-cooled cold plate is usually the next option. Here, the name of the game is minimizing thermal resistance, and pressure drop is usually less of a concern. Metal foam outperforms virtually any competing cold plate solutions out there. The demonstration unit here consists of a 1 square inch copper foam core soldered to a base plate with an equivalent 1 square inch ceramic heater soldered on the backside. Using distilled water as coolant at a flow rate of 2 liters per minute, this unit removes 500 watts of heat over that square inch of area while maintaining the base plate temperature at roughly 40 degrees Celsius above the water inlet temperature. This particular unit was made with 30 pores per inch foam compressed to a relative density of 30%. Performance can further be doubled, achieving 1 kilowatt per square inch of heat removal by using 45% relative density compressed foam. With liquid-cooled systems, you not only need to draw heat out at the heat source, which is typically an electronic component, but also need to reject that heat to the environment, typically with some kind of air-to-liquid heat exchanger. Shown here on this slide is a compact ram air-to-liquid heat exchanger for an aircraft avionics cooling application. Larger pore size uncompressed foam was used on the air side to minimize ram drag, while small pore compressed foam was incorporated into the thin liquid channels. In airborne applications, size and weight are both at a premium, and this 130 kilowatt unit measured only 13 by 17 by 1¼ inches and weighed roughly 30 pounds. And here we have a case study on metal foam phase change material heat exchangers from the European Space Agency's ExoMars mission in 2016. As with most space applications, thermal management is limited by the area available for radiating heat into space. However, much higher peak loads can be accommodated using a phase change material, typically a paraffin wax, that absorbs the peak heat loads as it melts and then solidifies or recharges during periods of lower dissipation. This cycle is illustrated in the notional plot below, and it allows sizing the ultimate heat sink based on the average thermal load rather than the peak load. The trouble with most phase change materials is that they have a very low thermal conductivity. For this application, ERG Aerospace designed 3 phase change material heat exchangers using dual-cell aluminum foam as a conductive metal matrix that was infused with the phase change material. This resulted in a 10-fold increase in effective thermal conductivity and less than 4 degrees of temperature gradient at all times. Finally, the application of metal foam in liquid vapor two-phase heat transfer is just emerging. The combination of high surface area and enhanced mixing holds great potential for improving the overall thermal performance of any two-phase heat transfer system, ranging from passive thermosiphons to pumped two-phase to vapor compression systems. Furthermore, in any two-phase heat transfer system, there exists a limit on the maximum heat flux, the so-called critical heat flux, which is associated with too much vapor coalescing near the heated surface and obstructing heat transfer. Phenomena described as departure from nucleate boiling and dry out can quickly result in overheating of the component being cooled. Therefore, the small hydraulic diameter and tortuous structure of foam can be very beneficial for dispersing the phases and extending the critical heat flux limit. While there have been some recent investigations in the area of two-phase heat transfer with foam, such as this work on the left, showing pool boiling with significantly lower superheat temperature for a given heat flux, or the flow visualization on the right showing phase dispersion at different flow rates, there are still many unexplored opportunities. Particularly with regard to flow boiling, where most efforts have thus far been limited to large pore size uncompressed foam, the most exciting research is still ahead of us. We hope this has been an informative introduction to metal foam and that we have sparked ideas for how metal foam could address your heat transfer challenges. We have a great team at ERG Aerospace with decades of experience producing metal foam and applying it to solve thermal problems. We would be glad to address any questions on this subject.
Okay, audience, please continue to get in those questions, and we'll get started with our first one here. Can foam be used as a straight heat sink without forced air?
Hi, this is Denver, and I'll take that question. Yes, it actually is used quite frequently as a heat sink, kind of a natural convection heat sink. We've found that it works very well in quite a few high-performance LED situations. We've done a couple applications and some case studies for drone applications for videography lighting. So it certainly can be used as just a natural convection heat sink. Naturally, the performance does increase if you use forced air and then go to liquid, but it certainly does function as a heat sink.
Okay, I have another question here. Both compressed and uncompressed foam show slightly significantly lower thermal conductivity comparing to that of a solid material in the same material. Where is the difference coming from?
A good question. This is Metodi. I'll take this one. So when we talk about thermal conductivity of foam, we're looking at the effective thermal conductivity of the bulk material, not the parent alloy. So when you have a porous material that is mostly empty space, the effective conductivity will be lower. In fact, the effective conductivity of fins or a finned core is also lower than the parent material. It is only when you look at the individual fins locally and look at just the conductivity within each fin that you will, then you're talking about the actual conductivity of the parent alloy.
Okay, next we have, what is the minimum pore size for heat transfer applications?
Hi, this is Denver again. I'll take that one. So really what we specialize in at ERG and kind of the advantage of metal foams is that we can customize that. So typically there isn't a standard minimum pore size. We look at the full thermal picture, kind of the size, the dimensions, the flow rates, the amount of heat you're trying to remove, and then we customize the material to meet that particular application. So sometimes that might be for a natural convection heat sink, we might be in a more open pore size, like a 10 or a 20 ppi. And then if we're into a forced convection or liquid cooling, we'll look at a smaller, more tightly packed. And then again, in liquid, we'll look at compressing the foam and making that pore size even smaller. So that's something that we specialize in, is looking at the complete picture and then customizing the structure for that particular application.
Okay, I have another question here, also related to the porosity range of metal foam. What is the porosity range of metal foam?
Okay, yeah. So porosity is essentially the void fraction or the volume fraction of empty space. And uncompressed metal foam can be produced with a porosity up to about 85%, which if you think about it in terms of relative density, as I often like to do, I like to think of it from the point of view of the metal content. That's about 15% relative density. Now that is just uncompressed foam, and as was noted in the presentation, you can really change that dramatically by mechanically compressing the foam. So then you can take it to, with compressed foam, you can go all the way up to about 50% porosity.
Okay, great. We have a question here. Do you see any applications in EV battery packs?
Yeah, we do. We see quite a few different applications across many ranges, but we have different metal foams for different parts of EV battery packs. So kind of the multi-function of the material is we have some for energy absorption. We do quite a bit for heat transfer. And then with our carbon foam, we actually use the carbon foam as electrodes in EV battery packs. So kind of just beyond the normal heat transfer aspect of it, there's quite a few other applications for metal foams. And then as we get beyond the metal foam and we look at the carbon and ceramic, some other applications there as well.
All right, next I have a question. What considerations should be made to minimize fabrication and layup efforts, and therefore part cost, when it comes to brazed interfaces?
Yeah, so this is something that we've also developed over our more than 50 years of manufacturing, and there's some considerations that we do when we look at it from a design for manufacturability standpoint. Quite frequently, it's actually easier to braze metal foam than it is small pin fins. The metal foam being a complete structure and the fact that it is compressible allows us to simplify the braze setup and ultimately lower part cost.
Okay, next, what is the recommendation for filtering of liquids to avoid clogging in the metal foam?
That's a good question. We typically would recommend filtering out particle sizes that are about half the average pore diameter. As you can imagine, there's some distribution of pore diameters within the foam, and so for example, for a 40 ppi foam, the average pore diameter is about 1 millimeter. So we'd want to filter out at least anything bigger than 0.5 millimeter. And that's for uncompressed foam. When you get into compressed foams, that obviously gets, that requirement is more stringent, and that kind of has to be considered on a case-by-case basis, depending on compression level and the details of the application.
Okay, next I have a question. How is foam applied to two-phase cooling?
So for two-phase cooling, hopefully we gave some examples in our last slide, but basically you can look at both pool boiling and flow boiling, and there's opportunities for foam to help in both. So in pool boiling, you're essentially adding a lot more surface area and a lot more nucleation sites, while also disrupting the film of air that can form, or vapor that can form near the heated surface. So you delay film boiling. With flow boiling, somewhat similar. You're adding a lot more surface area, and you're also helping disperse the phases so that you don't get large pockets of vapor that disrupt heat transfer.
Okay, the next question I have is, how uniform is the foam after compression?
That is also a good question. So it is quite uniform as long as you compress it by about a factor of 2 or more. So initially, when you start compressing, you tend to see one side of the piece start to compress first. But by the time you reach about 2x compression, there's no discernible variation through the thickness. We often compress large blocks of foam as starting stock for cutting and machining smaller pieces. And those smaller pieces do not vary in density or relative density any more than the natural variability found in uncompressed foam.
Okay, the next question is, how strong is the foam in tension, and what kind of pressure can foam heat exchangers withstand?
So the tensile strength depends on the relative density and also the compression level. Generally, for most applications, the yield strength is between about 100 and 500 psi, but that's for uncompressed foam. Once you start compressing, your strength increases proportionally. So 1,000 plus psi yield strength is common.
Okay, and our next question is, what is the variability in the foam manufacturing process?
So foam is characterized by its nominal force per inch, or PPI, along with the relative density, or conversely, the porosity. And there's about, so for relative density, which again is the metal volume fraction, there's about a plus or minus 1 percentage point variation within each large block of starting material. So when smaller pieces are being machined out of it, the final density can vary by about plus or minus 1 percentage point. So if we're, for example, if we're targeting a 7% density foam, we would typically specify that as a 6 to 8% acceptable range. Tighter tolerances are also common, but that does result in higher scrap rates. And then for pore size, for PPI, the value is also nominal, and there's some natural variability across the material with actual pore size. And this is a bit harder to quantify since rigorous measurements based on CT scans, CT scan data are still being accumulated. But generally, pressure drop, which strongly depends on pore size, varies on the order of about 10% if you're using consistent measurement setups.
Okay, well, we're just about out of time, so we'll go ahead and end the questions here. Thanks again to Metodi and Denver for their helpful presentation on this important topic. Don't worry if we didn't get to your question. All of the questions submitted will be posted on our website along with answers. Also, please check your email because in about 24 hours, you'll be receiving a message with a link to the on-demand version of this presentation. Our next session will begin shortly and covers thermal management for the connected world of IoT devices. We hope to see you there. I'm Jennifer Arroyo with Electronics Cooling. Thanks again for participating in Thermal Live.